Hi, my name is Xiao Li, and I'm a assistant professor at the University of South Florida. I'm very glad to host this TFTC webinar series on ISTTT 21. And thank all of you for attending this webinar today, and I really appreciate that because I know for some of you that this time is kind of difficult. It's very nice to have you all here. I want to thank Dr. Jack Haddad from Technion Israel for this sponsorship to this webinar platform, and Dr. Jorge Lava from Georgia Tech for organization, and also my PhD student Mohsen Pesafard for tech help. And I would humbly ask each one of you to mute yourself if you don't, unless you want to raise a question or make some comments. So the way to mute yourself is if you take a look at your control panel, the left to the control panel there is a small icon strip or icon bar, and on that there is a microphone icon. If you click it, it's going to toggle on or off your microphone. So muting it will definitely help minimize the background noise while the presenter is proceeding. This session will roughly have about 40 to 50 minutes of presentation time, and the remaining will engage Q's and A's. So I would encourage you to directly speak out. So just unmute yourself and put out your question from the microphone, or if you want, you can use the chat box all the way down on the control panel. So, but when you use the chat box, please make sure that you send your message to organizers and panelists only. This way everybody will see it. And okay, so the whole presentation process is being recorded. Just for your information, I start the recording. And okay. So today we're glad to have a talented young scholar, Dr. Kun An, as our speaker. She's a postdoctoral she's a postdoctoral researcher at the University of Illinois at Urbana and Champaign right now. But as far as I know, this is probably one of her last days there, and she's going to move to Monash University in Australia to join their faculty. Congratulate her on this great move in her career, and best wishes to her work and life in Australia. So Dr. Kun obtained her bachelor degree in transportation engineering from Tongji University, China, and a PhD degree in civil and environmental engineering from Hong Kong University of Science and Technology. Her research interest lies in transit network design, considering demand uncertainty and logistics, and supply chain design, and active control of signalized intersections. So today, I believe she's going to talk about design of robust design of transit network, considering demand uncertainty and development density. Without further ado, let's welcome Dr. Kun An.
Thank you, Xiao. Thank you. Thank you for having me here. Actually, today is my last day in University of Illinois at Urbana-Champaign. I'm leaving this night. Okay, I'll just start. Today I'm going to present our earlier work on robust transit network design under demand uncertainty, considering development density. This is a joint work with my advisor during my PhD studies, Professor Hongkan Luo from the Hong Kong University of Science and Technology. First, I will give you a brief introduction on my research background and literature review. Then I will introduce our research objectives. Then I will formulate a robust model for this transit network design, followed by a case study conclusion sections. So the transit network design problem, TNDP, is to decide the location of main stations, the route alignments, as well as the route frequencies to serve the travel demands in the most cost-efficient way. Well, in stochastic transit network design problem, they typically assume that the demand are stochastic. It either follow a certain distribution or captured by an uncertainty set, which can be solved by the stochastic programming approach or the robust optimization approach. In the previous studies, they typically take the OD matrix as given, but few studies have ever traced back to the population density that generates the OD demand in the first place. We know that the population density has great influence on the sustainability of rapid transit lines. Due to its high construction and operating cost for a newly developed region, the initial residential density may not be large enough to support a rapid transit line. So the government thus must be very prudent on how to develop rapid transit services and the sequence in constructing different lines. So we can see that in this figure shows the MTR construction sequence in Hong Kong from 1980 to 2019. We can observe that the network is becoming denser with the population increases. Another challenge we face is the demand growth uncertainty, which makes it uneconomical to rely on rapid transit lines alone. And ignoring the uncertainty often results in system over-design. So, those two challenges. In this study, we introduce another service called the dial-a-ride services. They are able to utilize the existing road network, thus having lower capital cost comparing with the rapid transit services. But it has higher unit cost and may incur higher external costs, such as congestion and pollution cost. So the objective is to find out the critical population density when the first rapid transit line is built. And we also want to investigate the construction sequences as the population density gradually increases. So intuitively, for a region with low residential density, it may be better to rely on dial-a-ride. Well, with the increase of the density, the congestion effect of the dial-a-ride becomes severe, and it may not be economical anymore to heavily rely on dial-a-ride. And that is when RTL comes into the picture. And we assume that the passenger discomfort on rapid transit services is represented by this nonlinear type of function. And the travel time cost on dial-a-ride services is represented by this BPR type of function. We consider the cross-mode user equilibrium between those two modes. And we consider the stochastic demand is captured by a polyhedral uncertainty set. Thus, we will propose a robust modeling framework for this transit network design problem and the demand uncertainty, while considering the cross-mode user equilibrium. First, let's look at how to map from the population density to OD demand. The density saturation gradient model is utilized to represent the evolutional process of population density. As shown in this figure, the x-axis is the distance to CBD, so CBD is located at 0. And the y-axis represents the population density. So the density at CBD is fixed at D0. This curve states that the intensive land use declines as the distance to CBD increases. And eventually, the higher downtown density and the low suburban density tend to equalize over time. So first, given a density factor, that is, the shape of this curve is given, then we can calculate the total population by integration. So the area below this curve is the total population. And then given the trip production factor as represented by this dotted curve, so this point is a candidate station location. We assume that the trip production ratio declines as the distance to the candidate station. So this curve shows like a Christmas tree. And then with the trip production ratio, we can calculate the total trip productions. And then we are going to distribute the trip productions to different destinations according to their attractiveness by a gravity model. So the attractiveness of CBD area is higher than the attractiveness of suburban area. So finally, we can obtain an OD matrix. The element Qij in the OD matrix denotes the average or mean of demand from node I to node J. Now we are ready to incorporate the uncertainty. We assume that the stochastic demand, the stochastic demand is defined in a polyhedral uncertainty set. To understand it, we start from a box uncertainty set. You can see those two simple examples with only two parameters. So the box uncertainty set only set bounds for each stochastic parameter by a lower and upper bound. Well, the parameters are independent to each other. You can see that the parameter for each one parameter, they can take any value in their within the lower and upper bound. Well, in the polyhedral uncertainty set, it incorporates a joint constraint. So the parameters are not independent anymore. You can see there is a joint constraint. So in our problem, the stochastic demand is bounded within a lower and upper bound. And we also incorporate a joint constraint that limit the total passengers heading for the same destination by an upper bound. So it means that this is more realistic. For example, the total demand arriving at the working center is limited by the amount of job positions, or the total customers to a commercial center is limited by its parking places. So that is to say, the demand for OD pairs are dependent now. They are not independent anymore. After demand generation, we now come to the network representation. To integrate the two service types, the rapid transit services and linearized services, into one multimodal network, we first segregate each node into three subnodes: station subnodes, the rapid transit line subnodes, and the linearized subnodes. Take this one, take candidate station A for example. A0 is the station subnode, A1 is the rapid transit line subnode, A2 is the linearized subnode. The subnodes are interconnected with each other. Passenger demand are imposed to the network through station subnode A0. And the blue lines allow passengers to board to rapid transit services or linearized services. And the black lines are transfer arcs between those two modes. And A1, B1, C1 are connected by the rapid transit arcs. The flow on those arcs represent the amount of passengers taking rapid transit services. And similarly, A2, B2, C2 are connected by the linearized arcs, with its flow represent the amount of passengers taking linearized services. Okay. And this network reformulation enables us to represent the passenger transfer time, waiting time, on-vehicle travel time conveniently at a link cost. The decision variables involves the station location variables. If WI is equal to 1 if a station is constructed at the candidate location I. And the road alignment variable YIJR is equal to 1 if link IJ is constructed on line R. And the frequency variables and amount of linearized services deployed. So the objective is to minimize the total system cost, which contains 4 components. The transit operating cost and line and the station construction cost, the linearized service cost, and the passenger travel time cost. Subject to a set of constraints, such as the transit line connection constraints, station selection constraints, frequency boundary constraints, and VI constraints. VI constraints are used to capture the UE condition. And we can see that this is the travel time cost on linearized services, and this is the passenger discomfort cost on rapid transit line. And a passenger flow conservation constraint. In these constraints, please note that the stochastic demand QD is involved here. The stochastic demand belongs to a predetermined uncertainty set. So we can see that this is the mixed integer nonlinear problem with equilibrium constraints and the stochastic demand. We first need to linearize this problem to make it solvable. As mentioned, the passenger travel time on their ride is represented by this BPR type of function, which only involves one decision variable, that is the amount of their ride services, Z, or the amount of passengers on their ride services. So we approximate this nonlinear curve by a piecewise linear functions. So by a piecewise linear function, through introducing binary variables, we can identify the active segment that the flow falls into. Then we can use this linear function to estimate the travel time on their ride services. But for rapid transit services, we can see that the passenger discomfort on rapid transit services is captured by this function, which involves 2 decision variables. One is the flow variable x, the other is the capacity of the rapid transit line. In both numerator and denominator. So we separate the domain into triangles. Okay, like this. This is the flow. This is the capacity of the rapid transit line. We segregate the entire feasible region into a set of triangles. So the goal is to identify the active triangle that the flow and Y fall into. So the passenger discomfort or the passenger travel time on rapid transit can be calculated by the convex combination of the 3 points of this active triangle. And another thing we need to address is the constraint 5, which involves the stochastic parameter. So by applying the strong duality property, we can derive equivalent linear constraints with this dual problem. I will not go to the details about the proof. So until now, the robust formulation is the mixed integer linear program and is readily solved by Cplex. But please note that the global optimization solution, we can actually obtain a global optimal solution, but the accuracy of this one is subject to the accuracy of the discretization. However, the number of extreme points in the VI could be huge, which makes the MILP often too large to be handled by the commercial solver. So instead, we adopt the cutting constraint algorithm to add the extreme points iteratively. This is a pretty standard way. So we first solve the relaxed MILP with a reduced number of extreme points. And additional extreme points can be found by identifying any feasible solutions that satisfies constraint, and which is equivalently transformed into a maximization problem. And whenever we find the objective function f is greater than 0, we can use this optimal solution as another extreme point and add this extreme point to the original problem, and which makes the initial solution infeasible. Then we can repeat this process until no extreme point can be found. And please note that when a new VI constraints for another extreme point is included, the solver actually can make use of the current solution as a starting point, which can greatly improve the expedite the searching process. We illustrate the formulation by a small case study. We use a linear network with 8 nodes from CBD to outskirts. We have totally 8 by 8 OD pairs. So CBD is located at node 1, and the suburban area, we assume it is located at node 8. So there are totally 8 by 8 OD pairs. The total population increases from 200 to 8,000 with a step size 200 to find the critical population. So for each total population, we can use the 4-step model to get the one average demand matrix, and this QIJ is the demand average. And then we assume this one is captured by a polyhedral uncertainty set. We considered 3 population distribution patterns. In pattern 1, in type 1, the population density gradually decreased from CBD to suburban area. And in type 2, we assume uniform distribution everywhere from CBD to suburban. And under type 3, we assume there are high density at CBD and new towns, but low density in the middle. So in this figure, this axis is the x-axis is the total population. It gradually increased from 200 to 8,000. And with the total population increases, the population density, of course, will also increase. And the y-axis is the cost. The red arrow indicates indicates the population when the first rapid transit line is built. And the blue arrow indicates the time when RTL covers the whole city range. That is, all the 8 nodes are covered by rapid transit lines. So under type 1, recall that under type 1, the population is clustered in the CBD area. We can see the first RTL is built quite late under type 1, and they are constructed earlier in type 2 and type 3. This indicates that a dispersive population distribution will be more favorable for constructing rapid transit line than concentrating the residents in CBD area. That is probably because that if we cluster the population in CBD area and the jobs, the work positions are also located in CBD, then they do not need the rapid transit line to commute. So it's like there are more intra-zonal trips. And the distance between 2 arrows represents the RTL construction time duration. We can see that a uniform distribution pattern under the PDP type 2, it requires a longer time to finish the whole RTL network, while a much shorter time is observed for population dispersed to both ends. For the RTL construction pattern, we can see that the type 1 observes a construction from CBD to suburban area, while type 3 have a reverse construction sequence from the suburban area to the CBD area. For type 2, the RTL construction will start from the middle, then gradually expand to both ends, to CBD or suburban. We understand that the RTL must be constructed on the most congested road segment. So under this type 2, when residents are uniformly distributed along the study area, then the road segments in the middle will attract the most passengers. This phenomenon is incurred by the exponential distribution of the destination attractiveness from the CBD to suburban, which means the attractiveness exponentially decreases from CBD to suburban. So it indicates that the demand generated from node 4 to node 8 will head for node 1 to 3. Well, the demand generated from nodes 1 to 3 will mostly be absorbed by themselves. Hence, most OD demands has to traverse the middle row segments, but not the segments at both ends. But under type 3, since high residential population in suburban area, will make the row segments at the right end congested. Hence, the construction will start from the right ends. To investigate the impact of direct cost on rapid transit line construction, we calculate the critical population under different direct cost ratios for 3 population density types, for 3 population distribution pattern types. So we can see that when this ratio is less than 1, from 0.2 to 1, which means the direct cost is direct services are cheap. Okay, so but we can see that this critical population does not change with the cost ratio, which seems to be counterintuitively, but it can be interpreted in this way. So when the population density reaches a certain amount, when it's large enough, it is not economical to rely on direct alone, even the direct cost is very cheap. Okay. So, but when the ratio is greater than 1, increases in this ratio, when the direct services are becoming more and more expensive, then the critical population density gradually decreases, which means the rapid transit line appears earlier. So, in summary, the higher direct cost, operating cost, will encourage the introduction of the rapid transit line. But a very low direct operating cost was not able to detain the rapid transit line construction. So when road congestion is severe, the RTL construction is imperative, regardless of the direct cost. So in this study, we formulated the robust transit network design problem under demand uncertainty. We traced back to the population density instead of using predefined OD matrix. We address the stochastic demand by robust optimization. We combined RTL services and direct services in one multimodal network, and consider the crowdedness on RTL services and the congestion effect, the road congestion effect of direct services. The cross-mode user equilibrium is also studied. In the future, we would like to investigate the influence of the network topology on the line construction sequence. Currently, we only consider a very simple network, a linear network. And in the future, we would like to investigate the gray network and the star network and so on. And currently, we study this problem from the perspective of the whole system. In the future, we would like to investigate the problem from the perspective of passengers, or the rapid transit line services companies, or the direct company, or from the perspective of the government. So that is all for my presentation today. It seems that it ends pretty early. So if you have any questions, I'm happy to answer it. Thank you.
Thank you, Dr. An. Particularly despite being in the midst of your hectic move to the new stage of your career. Very nice presentation and very, very solid work. I apparently enjoyed your presentation. I hope everybody else did. So we apparently have plenty of time to entertain some questions, and I'll mute all of you at this time. But if you don't want to raise a question at this point, you can stay muted, so this way everybody else can hear the audio in better quality. So the way to raise a question is, of course, first unmute yourself and um, speak out from the microphone. The second way is, or if you need time to organize your question, please use the chat box. The last, I think that's the last item or menu bar on your control panel, and make sure that when you send out your chat message, please send it to organizers and panelists only, and this way everybody will see it. So, and today we got a pretty good attendance, and I saw some names from familiar friends. So I hope you actively exchange your thoughts and suggestions with Dr. An. And yeah, sure, please feel free to raise your questions at this point. All right, I hear someone's typing. It's probably they're organizing their thoughts from the chat box. So maybe I can start with something so people can raise better questions and greater ones. So let's say, Dr. Ann, I think it's a really smart treatment to linearize the nonlinear BPR functions for both dial-ride and rapid transit line. And you mentioned that the error is the objective estimation error is related to the resolution of that discretization. So I guess it's intuitive that more coarsely you dice the segments or you partition the segments, so the more error you're going to have. I'm just curious. Actually, I'm learning on this as well. And as I'm just curious. It's not about your work, but are you aware of any other work that does a quantitative analysis about the error bound based on the way you discretize a problem? Or is there any relationship between like objective error and your discretization resolution in other work?
You mean the accuracy level associated with the discretization about the statistics work?
Yes. Yes.
To my knowledge, I'm sorry to say that I didn't see any work regarding on that issue. They are typically they just in their own study they try different numbers of different discretization numbers. Like we can separate into 100 segments or 1,000 segments, and then test the error comparing with the maybe the exact solution. But this pretty specific to their own study. For example, in my earlier work on a ferry service network, we also use this linearization techniques, and we tested like using like 50 segments or comparing with 1,000 segments, and we choose the number with acceptable error, such like within 5%. So, but for other people's work, I didn't see like much in this from this perspective.
Yeah, thank you. Maybe, yeah, it's a good way to test the error using numerical experiments, just to try to increase the number of partitions and see how when the results get converged. So that's a good way to prove that your discretization gets a good accuracy. I just feel like it's probably out of the scope of your study. I just feel like because it's linearization, it seems like you can, for one cost function, you can observe the worst case difference, right? For example, on the left, dollar ride service, the worst case error would be somewhere I believe between 8 and 1200 and 800 and 1200. If you do a search, you can find the maximum gap there, and that might give you some indication about the error bond. It could be a future research direction if nobody else has done similar work, like using this kind of element, so just a cost error from this graph to sort of imply the possible error bond of the functional evaluation. So that might be a possible future research direction. Anyway, yeah, just to
Yes, thank you. Yeah, this will be a very interesting, because if we know the upper bound or lower bound of the error, then we can like back calculate the segment size we need to reach that to keep the arrow into a certain bound. Yeah, that will be very
exactly,
interesting to do. Yeah,
yeah,
and we
that's
may not necessarily to discretize the whole region into evenly. We can do it like unevenly, then such that the error, the bound could not be like the maximum bound could not be too high. Yeah.
yeah, exactly. It could be a standalone question about how to partition your nonlinear functions to minimize the estimation error.
Yeah.
There could be some related studies, but I mean it can supplement the traditional way of using numerical tests, like the enumeration type of a numerical test, trying more and more numbers. It's yeah, exactly. You have good thoughts. Okay, so let's see. Any other questions? Okay. Well, I guess Dr. An has made this presentation self-explanatory and very clear. I understand pretty much most of the presentation. And thank Dr. An again for her nice presentation. And best wishes to her future career, and hope she's going to have a good settlement in at Monash University. With this, I guess we can adjourn today's presentation. Thank all of you for attending this webinar series again, and I hope you all have a good weekend. Next week, we're going to have Dr. Kahan from Britain to present his great work, and I hope you all can join this webinar again.